Alrighty, so we are back in Calculus BC and today we're taking a look at integration by parts. And this is just another integration technique where you get some sort of integral and you're like, I have no clue how to integrate that. And what you're going to end up doing is actually you're going to make two different substitutions. We've done u substitutions in the past. Today we're going to simultaneously substitute u for part of our equation and v for the other part. So what we're going to do is, instead of working with one really complex function, we're going to work with two separate functions side by side. And the reason this works is actually due to the product rule, and hopefully you've already read up on that. You've seen your integration by parts formula before. But the product rule tells us that if we have two different functions, where it's a function u times its differential dv, then we can split that apart, or rather we can take the integral, and the integral will become u times v minus the integral of v du. So notice we do still actually have an integral in our answer here. So we are going to actually take, there is a step further where you actually take the integral of this piece, but it's the hope that this integration here is much easier to integrate than the piece over here. That's why we broke it into parts. So really what we're doing is we're taking one original function, f of x dx, and we're splitting it into two different pieces, u dv. Now, figuring out what u is going to go in for and what v or dv go in for can be a little bit tricky. So let's look at a quick summary of what we're going to do first, and then I have two tips or tricks for you. So here's our friendly summary. We're going to split that original function into u, and eventually we'll need the derivative of that du. And this is just like normal substitution. We say u equals something, then we say du equals something dx. So it's nothing new there. But then the other piece of the function is going to be dv. And that's kind of like starting at the end, like starting with du. And eventually we know we'll need v, and to go backwards from du to u or from dv to v, we'll just have to integrate dv, and that'll tell us v. So it looks something like this. We're going to be given u, or we'll choose u out of the function. And then we will need du, but luckily du is easy to find. To find du, we just take the derivative of u. And then we're going to start at the end of the race. We're given dv, and we need to get back to the beginning. We need to get back to v, because we'll need that in our formula too. And to go backwards, it's easy enough. All we do is we just integrate dv. And this will give us four pieces to our puzzle. And when we put those four pieces together, we'll have the full picture. So we have these four, we're going to use them all. How do we do that? Well, sometimes deciding between u and dv for what you're going to substitute gets a little bit tricky. You're like, okay, I have some crazy function. I have x squared times the natural log of x times sine of x, so on and so forth. Which little piece of that am I going to choose for u? Well, generally, when you choose u, you want to think of the acronym LIATE. And LIATE stands for logarithms, inverse trig functions, algebraic functions like polynomials, x to some power, trig functions, and then exponentials. And we work from the L down or over to the E. So we're working left to right throughout the acronym. Whichever type of function you get to first is what u is generally going to be your substitution for. So for example, if you had something like x squared times sine of x, we have two different functions here. We have x squared and we have sine of x, and u is going to go for one of those. Well, going down, we'll say, do we have any logarithms? No. Okay. Do we have any inverse trig functions? No. Do we have any algebraic functions? Yeah, we do. We have x to some power, we have x squared. So in this case, we would choose u to be x squared, and then sine of x will probably be that dv. So if you can keep LIATE straight, it'll probably help you out with your u substitution. Though be careful, because this doesn't work every time. Maybe 90% of the time, 95% you're good to go. Other times you might try that first and get stuck and have to pick a different u substitution. It happens. Another tip or trick is that eventually you'll need to integrate dv. So when you're choosing your piece of the function that's going to be dv, you really need to make sure that it's something you can actually integrate. So if you're like, oh, okay, I'm going to let u equal 2, and then dv ends up being x sine of x ln of x times e to the x, and then you have to go to integrate it because eventually you'll need to find v, you'll end up getting stuck, and that doesn't really help you out. So u and dv work together to try to split this function apart into two simpler pieces. However, you will need to integrate dv, and really my suggestion would be choose the most complicated piece you can for dv, at least as long as you're still able to integrate there. Alright, however, this doesn't make a lot of sense unless we see some examples, so we have two examples for today, and let's get through it. Our first example is the integral of x squared times ln of x dx. And what we're going to need to do right at the beginning is figure out our u, our v, our du, our dv, our double substitution here. And we know that u is going to be given to us, as is dv. It's somewhere hiding up in this problem. We know how to choose u. We're going to use that friendly Lyautey acronym. We say, okay, we know logarithms are first, and we work through there. Well, we see in our function that there is actually a logarithm. So that's probably going to be our u substitution. So we'll set u equal to ln of x. We know, of course, too, that we're also going to have to find du. And du is just the derivative, the differential of ln of x, which becomes 1 over x dx. Usual u substitution, nothing weird. Now that we've chosen our u, we need to use the leftovers for dv. Our leftovers in this case are x squared and dx. We need to substitute everything out. So that means our dv is going to be x squared dx. In order to find v, we just work backwards. We say, okay, we have dv, we know to go backwards to get v, we just integrate. And integrating x squared is nothing super complicated. We raise the power by 1, throw that fraction in front to offset the new power, and we're good to go. So we have these four pieces, let's put them to use. And the way we're going to put them to use is using our integration by parts formula. A reminder of that formula might be a good idea. And it says that if you have the function u dv, that it's going to break apart into u times v, oops, I guess I should learn how to write a u times v minus the integral of v du. So now it's just a matter of fitting the pieces together. We can start with our original. We'll do it right underneath. Notice that u in this case is ln of x, so I'll write that first just to keep us straight. And then the dv that we picked was x squared dx. So that's going to break apart into u, which is ln of x, times v, which is 1/3 x cubed, minus the integral, we have v again, so 1/3 x cubed, du, which in this case is 1 over x, don't forget that dx. So it's a little bit unsettling to realize that you've taken something small and gone into a much larger expanded form, but realize that you've already done some integration here. So we've already actually done half the problem, and really we only need to focus now on the piece over here. So I'm going to suggest that we simplify a bit. Let's see what we get. I'll pull the 1/3 x cubed in front of ln of x. You don't have to do that, but it makes things look nice. We have this 1/3 here, which we can pull out front of the integral. And then notice we have x cubed times 1 over x. Well, x cubed divided by x will just reduce the power down to x squared dx. And we can go further now. 1/3 x cubed ln of x minus 1/3, and then the integral of x squared is something we should all be able to do. In fact, we did it earlier. It's just 1/3 x cubed plus what? Indefinite integral, so plus c. Maybe simplifying one step further, and I think we're done. We no longer have an integral in our problem, so we're not doing too badly. 1/9 x cubed plus c, and we're done. Notice a lot of the problems in your book, and every now and then you'll see this on the AP test too, might require you to go further. Maybe they'll want you to pull out like 1/3 from here, and then the x cubed might get pulled out in front. And it's just a matter of simplifying. Work at it till you get it, and you should be good to go. Alright, there's our first example. Pretty straightforward integration by parts. We incorporated Lyautey. Everything went pretty well. Now, the second one does show up on the AP test as well, and you'll have two of these for homework. And this one is affectionately called repeated integration by parts, for the good reason that guess what? You'll actually have to do integration by parts 2 times. So the integration by parts will simplify our integral a bit, but then we'll have to do it a second time to simplify further. So let's take a look at this. Integral of x squared times sine of x dx. Set it up the same way we did last time. We know that u through Lyautey, let's see, we don't have any logarithms, no inverse trig functions. We do have an algebraic function. That's our x squared. And working through, that tells us that du is derivative, so 2x dx. Now we start at the end and work backwards. We know that the leftover piece has to be dv, so I think this is our leftover, which is sine of x dx. And working backwards means we have to integrate that. Integral of sine is cosine, but remember the derivative of cosine is negative sine, so we need that extra negative on the front here. Take the derivative of cosine, negative, 2 negatives make that positive sign. Alright, let's apply integration by parts and see how we do. We know that we started with the integral of x squared sine of x dx. And in this case, it's like our integration by parts formula says. So we have to do u times v minus the integral of v du, which is 2x dx. And we can simplify a bit. It's probably a good idea. Get some color in there. So we can move the negative to the front, x squared cosine of x. Notice there's that extra negative we can pull out, and I'm also going to throw the 2 out front. So we get positive 2 times the integral of x cosine of x dx. And then we get sad, because x cosine of x is not the easiest thing to integrate, but it looks really similar to the beginning, so your thought might be integration by parts, and in fact you're right. Notice though that this power that we started with at the top has reduced by 1. Now we just have x to the first, which means this will probably be the last time we have to do it, which is nice. No AP problem is going to have you go more than 2 repeated by parts, so you should be okay. I'm going to go ahead and put this in a little bubble over here, just so we don't get too confused that we're kind of doing a little side note here. Maybe I'll put a star here. So, all I'm going to do is work with the integral of x cosine of x dx. And our substitutions are extremely similar to last time. Our u is going to be x, it's our algebraic function, which means du is just 1 dx. And then our dv is the leftover piece, cosine of x dx. And in order to get back to v, we just integrate, and this one's friendly, just sine of x, don't need any weird negatives or positives. So, integration by parts tells us that we can split this up into u times v minus the integral of v, which is sine of x, times du, which is really easy here. It's 1 dx, or rather just dx. And we can probably even go a bit further than this, since we can actually do the integral of sine of x. So we get x sine of x minus integral of sine of x becomes negative cosine, we'll throw that in parentheses, of x plus c. And even going a bit further, x sine of x plus cosine of x plus c. We got to be super careful here, because students tend to stop after this. They're like, oh, I had to do second integration by parts. I did it down here. I'm done. Well, you are, but remember that this invisible bubble here really just took care of this integral, and we still have all sorts of stuff in front of it. So I'm going to throw my equal sign back on there, and we have equals negative x squared cosine of x plus 2, and now we can insert this friendly bubble. X sine of x plus cosine of x plus c. And distributing gives us that negative x squared cosine of x plus 2x sine of x plus 2 cosine of x. And it's not necessarily wrong to write 2c, but 2 times a constant is just another constant, so maybe you can even call this c1 if you want, and then this becomes c2, or you can just say it's a constant. Nothing wrong with that. You don't have to simplify further if you don't want. I think the simplification would be kind of weird anyways, so I'm just going to end right here. So there's your second integration by parts. In fact, this was repeated integration by parts. Couple things to take away. Don't forget Liate. It'll help you choose that U. Make DV as complex as you can get it. And sometimes it doesn't work first try. Sometimes you may have to start over and choose a different U. Best of luck.